In this video, we'll be studying the electronic basis of chemical bonding. No one has ever seen inside the atom. Our theories about the internal structure of an atom are inferential, based on the experimental behavior of atoms. Suppose we wanted to know what was in our birthday present, but were forbidden to open it until our birthday. We could observe the size and shape of the box. We could weigh the box. We could shake the box, but we couldn't open it. After our experiments, we could produce a theory of what was in the box. That is essentially what we do with the atom. What is important to remember is that our theories of the internal structure of the atom give us a way of remembering the results of our experiments and a way to predict atomic behavior. Like a map in relation to its territory, our theories about the internal structure of the atom should not be confused with the internal structure. We produce quaint pictures of the insides of an atom as if we could gaze inside. We do this because we are visual creatures, and images help us organize and remember the results of experiments. But these images are not the same as the insides of the atom. In a previous video, we found that if we know the atomic number of an element, we can predict its number of electrons. The number of electrons must equal the number of protons in a neutral atom. Now we're going to study a theory of the arrangement of electrons inside the atom to account for the bonding behavior of atoms. To help us visualize the results of experiments, we will use an analogy of a hotel. We will place our electrons on different floors called energy levels or shells of our hotel, beginning with the bottom floor. The bottom floor can hold only 2 electrons. When full, we must put the remaining electrons on the second floor, which can hold 8. When the second floor fills, we must put the remaining electrons on the third floor, which can also hold 8. Let's look at an example. Calcium is element number 20 in the periodic table. That tells us that calcium has 20 protons, or positive charges, in the nucleus. It also tells us that calcium has 20 electrons around the nucleus. We will put the first 2 electrons in the first floor of our electron hotel. Next, we move to the second floor, where we'll place 8 electrons. This fills the second floor with electrons, so we must move to the third floor, where we place 8 more electrons. So far, we've placed 2 plus 8 plus 8, or 18 electrons in our electron hotel for calcium. We have 2 remaining electrons, so we'll place these on the fourth floor. The electronic configuration for calcium is 2, 8, 8, and 2. We can further simplify the electronic structure of an element like calcium by writing its symbol, capital C, lowercase a, and placing around that symbol the number of electrons in its outermost floor, the so-called valence shell. So we write Ca with 2 dots around it, symbolizing the 2 electrons in the outermost or valence shell. We do this because it is the electrons in the valence shell of an element that play the most important role in the chemical reactivity of the element. A general rule we can use to help us predict the chemical behavior of an atom is that an atom will react with other atoms in such a way to create a full valence shell of electrons. Let's check out the electronic configuration of element number 15, phosphorus. We place 2 electrons in the innermost shell, 8 electrons in the second shell, and the remaining 5 electrons in the valence shell. Note that the valence shell is short 3 electrons. So we would expect that phosphorus would behave in such a way to pick up 3 electrons from other atoms to achieve a full valence shell of electrons. Chlorine is element number 17. We place 2 of chlorine's electrons in the bottom floor of our electron hotel. The next 8 go to the second floor. The remaining 7 go to the third floor. Note the third floor, the valence shell for chlorine, is short 1 electron. We can predict that chlorine will behave toward other atoms in such a way as to fill its valence shell of electrons. Phosphorus is short 3 electrons in its valence shell, and chlorine is short 1. By sharing a pair of electrons with 3 chlorine atoms, phosphorus can complete its outer shell of electrons. Meanwhile, each chlorine atom picks up from phosphorus the electron it's missing from its valence shell. The result is a more stable compound, phosphorus trichloride. This reaction illustrates the general rule that atoms will gain, lose, or share electrons to create a more stable valence shell of electrons. Here is the periodic table of the elements. Recall that the fundamental organization of the table is based on increasing atomic number, beginning with the simplest of all elements, hydrogen, located here in the upper left-hand corner. The peculiar shape of the table reflects the desire to group elements in columns, representing similar valence electron structures, and therefore similar chemical behaviors. We refer to the rows of the periodic table as periods. So the uppermost period contains 2 elements, hydrogen and helium, which corresponds to the lowest level of our electron hotel, where we can fit 2 electrons. The second row contains 8 elements, beginning with lithium and ending with neon, which corresponds to the second floor of our electron hotel that fits 8 electrons. The third period begins with sodium and ends with argon, which corresponds to the third floor of our electron hotel that seats 8 electrons. In addition to these periods, we have elements arranged in groups or columns. The peculiar design of the periodic table allows us to group those elements together that have similar valence electron structures, and therefore will have similar chemical reactive behavior. That means the group headed by fluorine, which includes chlorine and bromine and iodine, will have similar chemical reactivity. Whereas group number 2, headed with beryllium and including magnesium and calcium, will have a different but yet similar chemical reactivity. Let's look at group 8A, the group on the far right, the group that contains helium, xenon, neon, argon, krypton, and so forth. The simplest member of group 8 is helium. Helium has an atomic number 2, which means it has 2 protons in the nucleus and 2 electrons around the nucleus. Both electrons will fit into the innermost shell, filling that shell, which means that helium is not going to be very reactive. Helium has a full valence shell of electrons, and so it has no need to pick up electrons to fill its valence shell. If we were to draw what is known as the valence electron dot structure for helium, we would write the symbol for helium, capital H, lowercase e, and put two dots beside it, each dot representing a valence electron. Helium is a stable atom. The next element in column 8, or group 8, is neon. Neon has atomic number 10, meaning it has 10 protons in the nucleus and therefore 10 electrons around the nucleus. We put the first 2 electrons in the first floor of our electron hotel, leaving us with 8 electrons for the second floor, which fills the second floor. We can write the valence electron dot structure for neon using the symbol for neon, capital N, lowercase e, and putting 8 dots around it, symbolizing the 8 valence electrons in its second floor. Note that the second floor is stable with 8 valence electrons, so we would expect that neon would be very unreactive. Its chemical reactivity is similar to helium. A third member of this group is argon. Argon is element number 18, so it has 18 electrons around the nucleus. We put 2 electrons on the first floor of our electron hotel, 8 electrons in the second floor, which leaves us with 8 more electrons for the third floor. If we were to draw the valence electron dot structure for argon, we would write the symbol for argon, capital A, lowercase r, and then we would put 8 dots around it, symbolizing the 8 valence electrons. Since the valence shell is full of electrons, we would expect that argon is going to be very unreactive. You'll notice that the members that we've been studying in this 8th group in the periodic table all have a full valence shell of electrons. In fact, all of these elements in this group are extremely unreactive. They're loners. They're called the noble gases because they don't readily associate with other atoms to form bonds. And that, in part, is why the periodic table has the peculiar shape that it does. The periodic law states that a group or column contains elements with similar chemical reactivity. So, group 8 elements, headed by helium, have a full valence shell of electrons. Group 7, headed by fluorine, is going to be short 1 valence electron. Group 6, headed by oxygen, is going to be short 2 valence electrons. Group 5, headed by nitrogen, is going to be short 3 valence electrons. So I think you get the idea that the members of each group have similar chemical reactivity because they have similar valence electron structures. Many of the most common elements follow what is called the rule of 8, or octet rule. Atoms gain, lose, or share electrons to produce a more stable valence of electrons. The most stable valence of electrons for most elements important for life is usually 8. Let's look at hydrogen, the simplest of all the elements. Hydrogen is element number 1, so it has 1 proton in the nucleus and therefore 1 electron surrounding the nucleus. You recall that the innermost shell can hold 2 electrons, which means that hydrogen is short 1 electron from having a full valence shell. So hydrogen needs to pick up an additional electron. Let's see what hydrogen can do to become more stable. Here is the valence electron dot structure for hydrogen. We use the symbol for hydrogen, capital H, with one dot beside it indicating the one valence electron. Suppose we bring in a second hydrogen atom. It also needs to pick up an additional electron to achieve a more stable configuration. So let's say they make a deal. One hydrogen says to the other, "If you let me borrow your electron part of the time, I'll let you borrow my electron part of the time. And then we can have a full valence shell of electrons." And so they consummate the deal. They form what is called a covalent bond, a sharing of a pair of electrons. And as a result, they reach a more stable configuration. But we no longer have elemental hydrogen. We have what is known as molecular hydrogen, H sub 2, two hydrogens covalently bonded together. A covalent bond is a sharing of a pair of electrons between two atoms. In the case of hydrogen, we can symbolize it with two dots between the symbols for the hydrogen atoms. These two dots represent shared pairs of electrons. We can also indicate this shared pair of electrons by using a dash between the two symbols for hydrogen. And we can also write it as H sub 2, molecular hydrogen. Let's look at chlorine, which is located in group 7 of the periodic table. Chlorine's atomic number is 17, which means it's going to have 17 electrons around the nucleus. We'll put the first 2 electrons on the first floor of our electron hotel. 8 will fit in the second floor, leaving us with 7 electrons for the third floor, the valence shell, which is short 1 electron. So chlorine has a need to pick up an additional electron. Here is the valence electron dot structure for chlorine. Notice that we have a vacancy, that is a place for an additional electron. Chlorine could share one of its valence electrons with a hydrogen if the hydrogen will share its valence electron with chlorine, and the result is a covalent bond, which we can symbolize by an H with a dash to the symbol for chlorine. The result is HCl, known as hydrogen chloride, or as hydrochloric acid. There are other things chlorine can do to reach a more stable configuration. For example, we could bring on a second chlorine atom. Since each chlorine is short 1 valence electron, they can work a deal to share a valence electron. And the result is molecular chlorine. 2 chlorine atoms with a dash connecting them. We can also symbolize it as Cl sub 2, molecular chlorine, a more stable structure than atomic chlorine. Let's look at oxygen. Oxygen is in group 6. It's element number 8, which means that oxygen will have 8 electrons. We put 2 electrons on the first floor of our electron hotel, leaving us with 6 electrons for the second floor, the valence shell, which means oxygen is going to be short 2 valence electrons. So oxygen needs to pick up 2 more electrons to have a more stable configuration. Here we have the valence electron dot structure for oxygen. We can bring on a hydrogen to form a covalent bond with the oxygen that satisfies the need of the hydrogen for an additional electron, but note that the oxygen is still short 1 electron. But suppose we bring in a second hydrogen and work a similar deal with the oxygen. Now there are 8 valence electrons around the oxygen nucleus. By sharing electrons with 2 hydrogens, oxygen has achieved a more stable electron configuration. We can symbolize this as oxygen with a dash connecting it to each of two hydrogens. We can also write it as H2O, which is also referred to as dihydrogen monoxide, or more commonly, water. Let's see what else we can do with oxygen. I've drawn the valence electrons a little differently because of the way we're going to be bonding with other atoms. We're going to bring on a second oxygen atom. Instead of sharing one valence electron from each oxygen, we're going to share two. We call this a double bond. We can symbolize it by two dashes between the symbols for oxygen. Each dash represents a shared pair of electrons. We can also write this as O2, molecular oxygen. This is the form of oxygen that we need from the atmosphere to survive. Molecular oxygen represents about 20% of the weight of our atmosphere. Let's look at nitrogen. Nitrogen is in group 5, and it's element number 7, which tells us that nitrogen has 7 electrons around its nucleus. We put the first 2 electrons in the first floor of our electron hotel, leaving us with 5 electrons for the second floor. And so the second floor, the valence shell, is going to be short 3 electrons. So we would expect nitrogen to be highly reactive. Let's see what we can do for nitrogen. Notice we've drawn the symbol for nitrogen with its 5 valence electrons around it. Why don't we bring in some hydrogens to see if we can satisfy nitrogen's need for additional electrons? Obviously, one hydrogen is not going to be enough. We're going to have to bring on a second hydrogen to share an electron with nitrogen. Still, that's not going to be enough. We're going to have to bring on a third hydrogen for an additional electron to be shared with nitrogen. Now there are 8 valence electrons around nitrogen and 2 valence electrons around each hydrogen. The result is a more stable configuration. As a result, we've formed a compound or molecule that we can symbolize in this form: nitrogen with lines connecting it to 3 hydrogens, each line representing a shared pair of electrons. Or we can write it more simply as NH3. The common name is ammonia. Let's see what else we can do for nitrogen. Notice I've drawn the valence electron dot structure for nitrogen with 3 electrons on one side. Why? Because I'm going to bring on a second nitrogen with 3 of its valence electrons on one side, and they're going to form what is known as a triple covalent bond. The 2 nitrogens are going to share not 1, not 2, but 3 pairs of electrons. The result we could write as N2, molecular nitrogen, which happens to be the most abundant gas in our atmosphere, representing about 78% of the weight of our atmosphere. Most of the air that we inhale is molecular nitrogen. We inhale it, and then in our next breath we exhale it. We have no biochemical use for molecular nitrogen from the air that we breathe. Let's look at this extremely important element of our bodies, carbon. Can you find carbon in the periodic table of the elements? Carbon is in group 4, and its atomic number is 6, which tells us it has 6 electrons around its nucleus. We can arrange those electrons by putting 2 in the bottom floor of our electron hotel, and the remaining 4 in the second floor, meaning that the valence shell is going to be short 4 electrons. What can we do? Well, here we have carbon written with its valence electrons. What we can do is bring on hydrogens to fulfill the need of carbon for additional valence electrons. One hydrogen is not going to be enough. Two hydrogens bonded to carbon is not going to be enough. Three hydrogens will still leave carbon short one valence electron, so we're going to have to bring in a fourth hydrogen to fill the valence shell of electrons of carbon. The result is CH sub 4, which is also known as methane, or natural gas. Let's see what else we can do with carbon. Notice I've drawn carbon a little differently here. I have drawn it with two valence electrons on each side. Now what I'm going to do is bring on an oxygen, and I'm going to form a double covalent bond between the carbon and the oxygen. Each atom is going to share two pairs of electrons. Now there are 6 valence electrons around the carbon, meaning it's still short 2 valence electrons. So let's bring on another oxygen and form yet a second double covalent bond with carbon. We can symbolize carbon bonded to 2 oxygens by 2 pairs of lines. Each line represents a shared pair of electrons. So we have 2 double covalent bonds connecting carbon to 2 oxygens. The result is what we usually call carbon dioxide, CO sub 2. We actually produce a lot of carbon dioxide in our body and blow it off to the atmosphere when we exhale. Let's see what else we can do with carbon. Here we're bringing on a second carbon, forming a covalent bond between the 2 carbon atoms. That's not going to be enough. That means there's only 5 valence electrons around each carbon nucleus. So why don't we fill in with hydrogens? And the result is C2H6, which is known as ethane. Or we can form a double covalent bond between 2 carbons. These 2 carbons are sharing 2 pairs of electrons. Still, there's only 6 valence electrons around each carbon. So we need to fill in with some hydrogens to produce a more stable configuration. Now each carbon has 8 valence electrons around it. And we can symbolize this by having 2 carbons with 2 lines connecting them. We call this a double covalent bond. And then each carbon also has single covalent bonds with 2 hydrogens. We call this compound ethene, and we can write it C2H4. Let's see what else we can do. Notice that I've written this carbon with 3 valence electrons on one side. What I'm going to do is to form a triple covalent bond between 2 carbons. So now there's 6 plus 1 is 7 valence electrons around each carbon. But each carbon is still short 1 valence electron. So we'll bring in some hydrogens to provide the missing valence electrons. And we can symbolize this by showing 3 dashed lines between 2 carbons, representing a triple covalent bond. And we can write this as C2H2, which is also known as ethine. Let's see what else we can do with carbon. I've drawn carbon with all 4 of its valence electrons on one side. I guess you can figure out what I'm up to. Going to bring on another carbon with its 4 valence electrons on one side, and we're going to form, yep, there it is, a quadruple covalent bond between 2 carbons. 4 pairs of electrons being shared by these 2 carbons. There is a wee bit of a problem, however. C sub 2 does not exist. At least, if it does exist, it exists only transiently. So basically, the quadruple covalent bond between 2 carbons, for all practical purposes, does not occur. The most covalent bonds between 2 elements that are abundant in our bodies is 3. Let's review the diversity of covalent bonds that we find in the molecules associated with life. A single covalent bond is holding hydrogen to chlorine. A double covalent bond is holding 2 oxygen atoms together. A triple covalent bond is holding 2 nitrogen atoms together. Carbon atoms can form single, double, and triple covalent bonds, but not a quadruple covalent bond. There is an alternative kind of bonding that can hold elements together. It's called ionic bonding. Let's see an example. Here we have sodium, which is element number 11. It has 2 electrons in the bottom floor of our electron hotel, 8 electrons in the second floor, but only 1 electron in the third floor, the valence shell. That's a problem for sodium because no atom can form 7 covalent bonds with other atoms. It would be like you trying to shake 7 people's hands at the same time. Let's bring on chlorine to see if we can solve sodium's problem. Chlorine is element number 17, so its electronic arrangement is 2, 8, and 7. Chlorine needs to pick up 1 electron to fill its outer shell, whereas sodium needs to pick up 7. Chlorine cannot solve sodium's problem by covalently bonding with it. But if it takes that lone electron from the valence shell of sodium, then chlorine can complete its outer shell while leaving sodium with a complete outer shell, its second shell. When chlorine takes the electron from sodium, it becomes chloride, a negatively charged ion. When sodium gives up an electron, it becomes positively charged, a monovalent cation. In electricity, opposite charges attract. So once chlorine and sodium ionize, they can bond to each other, forming what is called an ionic bond. Here's a summary of what just happened. Sodium gave up an electron to become sodium ion with a net positive charge. Chlorine picked up an electron from sodium and became a negatively charged ion, chloride. The sodium cation and the chloride anion were then attracted to each other's opposite charge to form an ionic bond, sodium chloride. Here's another illustration of the process. By accepting the lone valence electron from sodium, chlorine filled its outer shell while leaving sodium with a full outer shell. Then the opposite ions can bond, proving theft is not always a bad thing. The salt crystals in your salt shaker at home are aggregates of sodium and chloride ions, held together by the attraction of opposite charge. In review, we've seen two kinds of bonds that can hold atoms together. Covalent bonds involve a sharing of one or more pairs of electrons. Ionic bonds involve the attraction of oppositely charged ions. The covalent bonds are stronger than the ionic bonds and more difficult to break.